Today we're going to talk about identifying connections between quadratic expressions, specifically between quadratic equations and their graphs. In order to do this, we first need to understand that there are three different forms that we can write quadratic expressions in. The first being the standard form. For example, we have y equals ax squared plus bx plus c, where a, b, and c all represent numerical values. Factored form will appear as y equals a times the quantity x minus p times the quantity x minus q, where a, p, and q are also all numerical values. And our final form is vertex or graphing form, which is going to be represented by y equals a times the quantity x minus h squared plus k. So these are the different forms that all represent quadratic expressions. Now let's go ahead and talk about what each form is going to tell us about the graph of a quadratic. So our first form is going to be standard form. We have x squared plus 5x plus 6. Now if we want to keep it in this form, in order to graph it, we're going to have to create a table. So I've already gone ahead and drawn the table out for us. So if we take a look at this, what we notice is that our y-intercept, our starting value, happens when y equals 6. Now if we go ahead and look back up at our equation, 6 is our c value to our equation. And this happens because when we plug in 0 for both of our x values, we get 0 squared, which is 0, plus 5 times 0, which is also 0, plus 6. This tells us that our c value, when the quadratic is written in standard form, is going to be our y-intercept. So if we were given a bunch of graphs to look at, we can identify the correct graph by trying to identify the correct y-intercept. Now, if we want to graph the full thing, we're going to have to rely on creating that table. So we can create the table. We can go ahead and graph the other coordinate points that we were able to locate. So we have -4, 2, -3, 0, -2, 0, -1, 2 as well. And then because we have this reflection, we're also going to have that coordinate point -5, 6, if we wanted to go ahead and plot that. So we know our vertex is going to happen somewhere in the middle because of our line of symmetry being dead center. And in this case, our line of symmetry is going to happen at x equals -2.5, since that lies right in between our x-intercept values. So if we would like to find the exact coordinate point of our vertex, all we have to do is plug in -2.5 into our equation and solve for the y. So if we have -2.5 squared plus 5 times -2.5 plus 6, we will get 6.25 minus 12.5 plus 6. Then we can combine all of those together for a grand total of -0.25. So our vertex is going to lie at -2.5, -0.25. So we can go ahead and try to eyeball that point. And now we have a good sketch for our parabola. So once again, the standard form is going to give us the y-intercept of our graph. All right, moving on to factored form. So this is an example of factored form, y equals 3 times the quantity x minus 4 times the quantity x plus 2. So something to keep in mind, this 3 represents our greatest common factor when we are graphing. And it does not actually affect our x-intercepts when we solve for our x-intercepts using the zero product property that we have learned in class. However, it does affect how wide our parabola is. So we have learned in class and we've talked about factoring and then solving for the zero product property. And by doing so, we're finding the x-intercepts of our parabola. So if we go ahead and use that zero product property, I'll go ahead and write that. We're really solving for those x-intercepts. And all the zero product property is doing is it's telling us to take each one of these binomials separately and set them equal to 0. Because when we are solving for the x-intercepts, our y coordinate point is going to be 0. And so we really have 0 equals 3 times the quantity x minus 4 times the quantity x plus 2. And we know if we have 3 separate things, 1, 2, 3, and we multiply them together and it equals 0, at least one of those things has to be 0. Now we already know 3 is out of the picture because 3 does not equal 0. However, depending on what x variables we throw in here, x minus 4 could equal 0 or x plus 2 could equal 0. Once again, depending on what x equals. So we just need to find out what that is. So we're going to set up two equations, x minus 4 equals 0 and x plus 2 equals 0, and we're going to go ahead and solve for x. So over here we can add 4 to both sides, so x equals positive 4, and we're going to subtract 2 over here from both sides, so x equals negative 2. Alright, these guys are going to represent our x-intercepts. Once again, because we plugged in 0 for y, we know that we're solving for those intercepts there. So I can go ahead and plot negative 2 and plot positive 4 on my x-axis. So now we just need to locate the vertex. Once again, we know there's that line of symmetry in a parabola, so we just need to locate the dead center of our x-intercepts, which in this case is going to be negative 1. So we have this nice line of symmetry here at negative 1, and this is where our vertex is going to lie. So all we have to do is plug in negative 1 to the original equation to solve for where our vertex is going to be. So we have y equals 3 times, positive 1 minus 4 times 1 plus 2, which will give us 3 times negative 3 times positive 3, which will give us a grand total of negative 27. So our vertex is going to happen at the point 1, comma, negative 27. Now on our graph, depending on how skewed you want it, we can go ahead and draw out 27 tick marks. Let's see. All right, and we have our vertex point. And since we have our two x-intercepts, we have our vertex. We can go ahead and sketch our parabola. Now notice how it's a lot skinnier than most parabolas. That is because of our greatest common factor of 3. The larger the greatest common factor, the more narrow your graph is going to be. And the smaller, the closer to 0 your greatest common factor is. So for example, 1/2, 1/3, 1/4, the wider the parabola is going to be. All right. Our final form is going to be known as the vertex or graphing form. And the name kind of goes ahead and gives it away as to what this form tells us. It tells us the vertex of the graph. And how we identify the vertex of the graph is by looking at our h and k values. So let's go back to the general form of the equation. It was y equals a x minus h squared plus k. So that minus h is really important. It's going to tell us that we need to take the opposite of this value. And the reason why it's a plus is really we're throwing a double negative into the equation. So if we have x minus negative 5, our double negative is going to make that a positive. Ergo our plus 5 in the equation. So our vertex for this graph is going to happen at negative 5, 3. So we can go ahead and plot that point. Now, in order to sketch the rest of this graph, we do need to look at the a value. Since our a value is negative in this case, that means instead of our parabola opening up, it's going to open down, since we do have a negative graph now. We also have what's called the step pattern that we have looked at. And one thing that we have noticed is the step pattern is all of the odd numbers when the a value is equal to 1. And the step pattern is how we go from one point to the next while graphing a quadratic. So from our vertex, our first step is going to be a 1. Because we're going down, this means we're going to travel over 1 and down 1. And this is going to reflect on both sides. Our next step value is 3, which means we're going to travel from the previous point over 1 and down 3 points. The next step value is 5, so we're going to, from this point, travel over 1, down 5. And then we can continue the step pattern as long as our graph permits us to. So depending on the size of your graph, depending on the context, we can continue that step pattern. But as long as the a value is 1, our step pattern is going to go up by the odd numbers, 1, 3, 5, 7, 9, 11, and so on and so forth. So this is how we can sketch a nice graph knowing the vertex form or the graphing form of a quadratic. So going back to the first slide, our standard form of the equation will tell us our y-intercept value. And the y-intercept value is going to be our c, our constant term. Our factored form is going to tell us the x-intercepts. And we find the x-intercepts by using that zero product property. And finally, the vertex or graphing form gives us our vertex. And our vertex is going to be identified by the coordinate point h, k. And that is how you can identify any connections between quadratic expressions and their graph.